Okay, Algebra 2, Chapter 3, Section 1. This is dealing with solving systems using graphs of system of equations. And system of equations are a set of two or more equations. A linear system is essentially a set of linear equations. A solution of a system, according to the book, it says it is a set of values for the variables that make all the equations true. You can say for the solution of a system is a set of coordinates that are the same for a system. Basically, what is the same x and y for each equation that is true for both. In essence, when we talk about linear equations, a solution to the system in actuality is their intersection. Where they both intersect. Or, their points over the intersection is also their solution. So for problem number 1, it says to graph the equations, the point intersection appears to be 4, -2 right here when you graph these guys. So you can graph them however you see fit, whether it's most likely using a graphing calculator. And when you see where they intersect, then that is their solution, or point intersection is the solution. Now, there's another way to do this using a graphing calculator to plot their point of intersection. What the book does is that it turns it into slope-intercept form, turns the second one into slope-intercept form. They plot the points or the equations into the graphing calculator, which you can do. And after they do that, they find a point at which they intersect. So for got number 1, we have x minus 2y equals 4. I can subtract x from both sides. -2y minus x plus 4, and then divide by -2. Y equals -1/2 x minus 2. So that's the slope-intercept form. And then for the second equation, I can plug in 3x plus y equals 5, subtract 3x from both sides, y equals -3x plus 5. No, I have two options. The first option I can do is I can graph these. Then find the intersection. Second step is I can graph these guys using a graphing calculator, or I can use a graphing calculator to create a table to find a point where they are at point of intersection. I could do it either way. So I'll turn them into slope-intercept form, graph them to find intersection, I can also use a graphic calculator to do that as well, or use a calculator to create a table to find a point of intersection. Either way will work. And I'll show you exactly what that means right now. So if you have a graphing calculator, it's going to look like this. So if I was to go back, it's -1/2 minus 2. So I'll go into right here, hit -1/2 minus 2. And then the second one would be, it was -3 plus 5. -3 plus 5. Here's what I'll do to save me time. Put this back over here. Okay, cool. Alright. -3 plus 5. Okay. Then I'm going to hit second and then table. Then it gives me a list of values. Oh, that doesn't look right. That's not right at all. So what I do? Oh, let me go back. -1/2. I'm going to hit this button here next to alpha, xt theta n. There you go. -2. There we go. And this is going to be hit x plus 5. Alright, then I'm going to hit second and table. And I have a bunch of points. And I'm going to try to find where the blue and the red are the same at the same time for the given x. So you're just going to sort of go through all of these until you find where they're the same, which is proving to be not going down. Eventually you'll find it. I'm not going to go through all of this to look for it, but that's how you're going to solve these problems. Okay. Using a table, same concept. For this guy, you have an equation, you create a table, and you find the age or the x such that they're the same y for each one. Very tedious task. Nobody solves problems this way. Alright, so definitions. Consistent. When you have a consistent system, you have at least one solution. Of those consistent systems, we can have two types of subsets of consistency. We have an independent system where it has one solution, and a dependent system where it has infinitely many. So we have the first two graphs here. We have a line intersecting another line only at one point. That point of intersection is your solution. That solution makes this consistent because you have at least one. And it's independent because you only have one intersection. The two lines are not the same. Here we have two lines, one right on top of the other. Since it has at least one intersection point, it is called consistent. And it's called dependent because it has infinitely many solutions because they're the same line. And remember, a line consists of many points, infinitely many points. So this is consistent and dependent because it is the same line right on top of the other. They intersect infinitely many times. This is consistent and independent because it are two separate lines that has one and only one intersection point. one solution, consistent, independent over here. Infinitely many solutions, consistent and dependent over here. Then we have something called an inconsistent system, and that's when you have two lines that are parallel. Two lines that are parallel. Oh, one line on top of the other is called coinciding lines. Coinciding lines. All right, parallel lines. We have two lines that are never going to intersect. Therefore, since they never intersect, they're never going to have a solution. Therefore, we call that an inconsistent system. All right, classifying a system without graphing. The easiest way to do it is to look at their slopes. So and to look at their equations, because they could be the same equation. So the easiest way to do these guys is to put these guys into slope-intercept form. And then once you do that, you should be able to tell whether they are consistent, inconsistent, consistent, dependent, consistent, independent. So for 3a or 4a, we have negative 3x plus y equals 4. So add 3x to both sides, so this is y equals 3x plus 4. Then on the other side we have x equals negative 1/3 y. Oh, x plus 1/3 y minus, rather. My brain. Equals 1. Add the 1/3 y, subtract the 1, so it'll be 1/3 y. So this negative 1/3 y equals negative x plus 1. Multiply both sides by negative 3, y equals 3x minus 3. Notice that the slopes are the same. So same slope. They have the same slope, but they have different intercepts. Same slopes, different intercepts. When they have the same slope and different intercepts, same slopes means that they're never going to intersect because their slopes are identical. So that means parallel lines. And since they're parallel lines, that means that they are inconsistent. Same slope, different y-intercepts, parallel lines, inconsistent. For B, we have 2x plus 3y equals 1. That's 3y equals negative 2x plus 1. Y equals negative 2/3 x plus 1. That's our first equation. Second one we have is 4x plus y equals negative 3. Y equals negative 4. X minus 3. Different slopes, different y-intercepts. This means that it's going to have one intersection point. Which means that it's independent and consistent. So it's consistent. It's independent. Consistent and independent. Different slope, different intersection, so it has that at least one intersection. Different y-intercept rather, so it has one intersection, therefore it's going to be consistent and independent. And then lastly, we have y equals 2x minus 3. It's already in slope intercept form. We have 6x minus 3y equals 9. Subtract 6x with negative 3y equals negative 6x plus 9 divided by negative 3y equals 2x minus 3. Notice that this equation and this equation are the same, so we have identical equations. So that means that it has many solutions because they're the same line. They're stuck on top of the other. So that makes it consistent and dependent because they are the same lines. Okay, so they're coinciding lines. Alright, so that's this section. I hope you have a great rest of your day.